Now, in today's lecture we shall start discussion on interpolation and approximation. Let us just define what we mean by interpolation, what we mean by approximation. Now, let us consider the case when we are given a data. So, the data could be a table of values. Now, the various types of data can exist. So, for example, I may have simply, if I take x as a variable and the f x as the dependent variable, I may have set of values given to me at a point x naught. I have been given a value of x naught, x 1 I have been given a value f at x 1 and so on. I have given these n plus 1 values. So, this is the values are given by x I f I, which I am denoting x I f at x I this, and these are n plus 1 points at which the data is given to us. So, I is going from 0 1 to n. Now, the problem is to construct a polynomial which fits this data. So, that shall be called an interpolating polynomial. To construct a polynomial which fits the data, and this is called the interpolating polynomial. That means, if the polynomial is say p x, then what we are saying is that p at x I will be equal to f at x I. So, this is what we mean by saying by fitting this a polynomial to the given data at n plus 1 points. So, the if I substitute x is equal to x I, I would get back my value of x I. So, it exactly fits the given data. Now, the use of the interpolating polynomial are many. One is I can estimate or predict the value of the dependent variable at any intermediate point from here. Let us say an experiment has been conducted in an intervals of say 15 seconds and you have done it experiment over a few hours. Now, you want to find out approximately what is the value of the dependent variable at a certain instant of time which is not one of these points. Then we will be able to predict the value of the dependent variable using the interpolating polynomial. Secondly, consider this as a point in a 2-dimensional plane. This is a point in 2-dimensional plane. It will represent a curve in the 2-dimensional plane. You may like to have the slope of the curve at any point. That means, you want to like to know dy by dx or df by dx at a point. Now, if I have the interpolating polynomial which is a function of x, I can just differentiate this by with respect to x and then use that for finding the value of the slope at any point, at any intermediate point or at these points also. Alternatively, you may like to integrate the function f x over this entire range. I can use this interpolating polynomial and again find the value of the integral from there. So, the purpose of the interpolating polynomial are many and its application is in many areas. The second problem is approximation. The problem of approximation is slightly different from interpolation. The problem of approximation is of two types. One type is that we have been given a function f x already. So, a continuous function is given. So, f x is given, f x is given and it has got certain properties, but the f x could be very complicated to actually find out what are the properties of this function, or like what is the maximum, what is its minimum, I mean how it is behaving. All these properties is unknown when its f x is complicated. What we would like to do is we would like to approximate f x in terms of known polynomials. The more known polynomials are mostly orthogonal polynomials. The orthogonal polynomials which we know are the Legendre polynomials, Chebyshev polynomials and there are other polynomials over the interval given in interval, we know the orthogonal corresponding polynomial. I would like to, when once f x is defined in a particular interval, I would suitably choose the orthogonal polynomials and then approximate f x in terms of those orthogonal polynomials, a finite series of them. So, therefore, the problem of approximation is that means to approximate f x in terms of known orthogonal polynomials. In terms of known orthogonal polynomials. Now, when once we approximate it, now since it is a known orthogonal polynomial, I know all the properties of orthogonal polynomials and hence I can be able to describe the properties of f x using these polynomials. So that the properties of f x can be studied. Now, we will come back to this problem and take the suitable interval and then construct this approximation problem. The second type of problem is that we are given a data, instead of a continuous function we are given a data. So, a data is given. Now, this data represents a function f x, but we do not know that function f x, but I would like to write an approximation to the polynomial f x which may be representing this data. For example, in the interpolation we can construct a polynomial exactly which fits the data. Now, I want to construct an approximation here which is an approximation to the f x which will be representing the data. That means, the approximation here is not fitting the data, it is only approximating the function which represents the data. So, this is an approximation to the function which represents the data. We are going to consider both of them through some simple examples also. We shall take it up and see how the approximation is useful for us and how interpolation is also useful for us. So, let us first start with interpolation. So, let us define interpolation. Now, here the Taylor series which you already know can be looked after as an interpolation polynomial. So, for example, let us describe how it is an interpolating polynomial. Now, we will take the given data as this. So, the given data is at x naught, f at x naught, f dash at x naught, so on, f n at x naught are prescribed. So, we are taking the ordinate f x naught and its first n derivatives, they are all prescribed for us. So, we have a data f n plus 1 values prescribed, this is n derivatives plus 1. So, there are n plus 1 values, n plus values are given. Then I can write down the Taylor series which is a polynomial of degree n at x as f at x naught plus x minus x naught f dash of x naught plus so on x minus x naught to the power of n by factorial n, nth derivative at x naught, plus of course r n x, we can write down the error also, plus r n x. R n x is the remainder, or we will call it as error. And the value of r and x, error is given by x minus x naught to the power of n plus 1 by n plus 1 factorial f n plus 1 plus some intermediate point xi where x naught xi less than x. Xi is a point between x naught and x which we are considering. Now, this Taylor series can be taken as an interpolating polynomial, but interpolating this type of data. So, the values at x naught are given at n derivatives, and then we can write down this as an interpolating polynomial. In all the interpolating problems, the error plays a very important role. The error will govern what is the step size that you can use in a particular data, or what is the step size you can use for a particular problem for solving it, or what is the error bound, what is the largest error which you are committing in a particular interpolation problem. You may be like given a data of say 1000 points, you may like to use only a set of few points to construct a polynomial. Now, what will be the error in that particular approximation or interpolation will be known through this error term, that is we have got here, or the remainder term. Therefore, we can always bound this. So, I can find the bound of the error as, so I can write the magnitude of r and x, that will give me the bound of this, that will be 1 upon n plus 1 factorial x minus x naught magnitude n plus 1 magnitude of f n plus 1 of xi. Xi is a point which is unknown for us between x naught and x. Therefore, we shall replace this by its maximum value. So, then I can write down this as less than or equal to 1 upon n plus 1 factorial x minus x naught magnitude to the power of n plus 1, and this I will write this as m n plus 1, and m n plus 1 is maximum of x lying between given an interval x naught to some b that is given to us as f n plus 1 of x. Now, we propose to use the Taylor series starting from the point x naught to a point b. So, the maximum of f n plus 1th derivative over the interval x naught to x b shall be taken as the quantity that we want to use it here. So, m n plus 1 will be the quantity that we will be using here. How we can use the knowledge of this error bound to say something about this Taylor series. Now, let us say that an estimate of m n plus 1 is available to us. Assume an estimate of n plus 1 is available. Now, a way of getting an estimate is, suppose you are asked to construct a 5 term Taylor series. So, let us suppose we are asked to construct a 5 term Taylor series. 5 term Taylor series means starting with this 1, 2, 3, 4, 5, that means up to 4th derivative. So, x minus x naught to the power of 4 factorial 4 f 4. Now, the remainder term will be of 5th derivative. So, what we do is to find an estimate of the required derivative of the 5th derivative. I will construct the Taylor series with one more non-vanishing term, that means one more term that we want. We want 5 term series. So, I will construct the 6th term which is a non-zero, because there may be many zeros in between. So, I will have the next non-zero. When once I construct the next non-zero term, I will now differentiate this required number of times and take that as an estimate, because you want a certain number of terms. So, we construct the next higher order polynomial, differentiate it the required number of times, and that can be taken as an estimate, because we want only a rough estimate of this. So, we will assume that an estimate of m n plus 1, this n plus 1 derivative is available. Let us say you want that the error should be less than some tolerance epsilon. So, this is our tolerance given to us. Error tolerance is given, some 10 to the power minus 4, 10 to the power minus 5 is given to us. Now, interestingly, this will then give us, let us write it here, this will be 1 upon n plus 1 factorial x minus x naught to the power of n plus 1 m n plus 1 is less than epsilon. Now, here if the tolerance is given to us and the number of terms that you have in the Taylor series, that is n describes the number of terms in the Taylor series, n plus 1 is the, if you have got a Taylor series of order n, number of terms are n plus 1. So, when if n is given and epsilon is given, then I can find out up to which point I can use the Taylor series with that accuracy, because we want to use the Taylor series from x naught to certain point b. Now, when once we are given epsilon and n, I can now find out what is this distance, what is this value x minus x naught, that will give me how far I will be able to use the Taylor series with this accuracy. Therefore, you can say given n and epsilon, we can find x minus x naught, that is the interval in which the Taylor series holds. In which the Taylor series holds. If you can represent this x minus x naught is equal to h, the distance h, then it is actually giving what is the maximum distance you can go from x naught, so that the Taylor series is valid with this tolerance of this. Or alternatively, we can say that if you are given the interval and tolerance, then this will tell me what will be the value of n. So, that means how many terms in the Taylor series you should take if you want an accuracy of say 10 to the power minus 6. So, I can say that this many terms, 10 terms, 11 terms, 12 terms should be taken in order that we have this particular tolerance. So, we can say given epsilon and h. So, this is the h which we are talking of, given epsilon and h, we can find n. The n is number of terms required in the Taylor series so that the accuracy epsilon is retained. Now, we are finding n, when once I find n, I will say the number of terms will be equal to n plus 1. The number of terms will be, because f at x naught is the 0th term. So, it will be total number of terms will be n plus 1 term that will be required in the Taylor series. So, a number of observations or number of conclusions can be made when once we have the remainder of this particular Taylor series. Now, let us illustrate these 2 points with an example. Let us take an example on this. So, let us say obtain polynomial approximation let us give the function to the given function. Let us take a simple function 1 minus x to the power of half over 0 1 by means of Taylor series. By means of Taylor expansion, let us take the point x is equal to 0, about x is equal to 0. Find the number of terms required in the expansion find the number of terms required in the expansion to obtain results, correct to 5 into 10 to the power of minus 3. For 0 less than x less than half, less than or equal to half. I am taking a particular problem, I am giving the interval and then say giving the accuracy also, and then asking what are the number of terms in the Taylor series that will be required in order to achieve this accuracy. So, the first part let us just do it, let us differentiate it and find out what are the values. We are given f x is equal to 1 minus x to the power of half. Therefore, f of 0 is equal to 1. Let us differentiate it, f prime of x is half 1 minus x to the power of half. I have taken the minus sign already outside, minus sign I have taken it. So, if I set f prime at x is equal to 0, I will get minus half. Let us write down the second derivative. So, this I will write it as 1 upon 2 up, therefore, this is plus and again a minus sign. So, I will have 1 upon 2 square 1 minus x to the power of 3 by 2. So, that second derivative is equal to minus 1 upon 2 square. Now, let us write down one more and then write down the series. Now, this is 3 by 2 with a negative sign. So, this is plus 3 by 2 cubed with a negative sign, that is 3 by, I will write 1 into 3 by 2 cubed 1 upon 1 minus x to the power of 5 by 2. So, that f triple dash 0 is equal to minus 3 by 2 cubed. Therefore, our series is f x is 1 minus x naught, x naught is 0. So, 1 minus x into, I will put it, let us put it here, 1 plus x into minus half, x minus x naught whole square by factorial 2, second derivative 1 upon 2 square, x cubed by factorial 3 minus 3 by 2 cubed plus so on. So, that I can write this as 1 minus x upon 2 x squared by 8 minus x cubed by 3 cancels, I will have 16 plus so on. Now, I need to find the nth derivative and I want to find the bound for this. So, I want to find r n x is less than or equal to 1 upon n plus 1 factorial x minus x naught, that is x to the power of n plus 1, and m n plus 1, that is maximum of the interval given to us is 0 half and I need n plus 1th derivative of x. Now, let us write down what is our nth derivative. Now, we have the expression, I have written this in a particular fashion. You can see this is the next derivative is going to be given me minus 5 by 2. So, I absorb this minus sign, always minus sign comes 1 3 then 5. So, I will have the products in numerator as 1 3 5 7 9 and so on, because this is 5 by 2 7 by 2 9 by 2 and so on, and the denominator becomes 2 cube 2 to the power of 4 2 to the power of 5 and so on. Therefore, my nth derivative is with a negative sign 1 into 3 into 5 into 7 into 2 n minus 1 2 n minus 1. This is 2 to the power of n plus 1 1 minus x to the power of 2 n plus 1 by 2. This is 3, this is 5 by 2. So, this will be 2 n minus 1 and this will be 2 n plus 1 by 2. This is our the f n plus 1, this will be f n plus 1. Let us find the maximum of this. I want the maximum of this in this interval. So, maximum in the interval 0 to half f n plus 1 of x is 1, 3, 5, so on 2 n minus 1 by 2 to the power of n plus 1. I need a minimum here, so that it will give the maximum of this. So, the minimum of this in 0 half will occur at half. I will have here 1 by 2 of this power, that is 2 to the power of 2 n plus 1 by 2. Now, let us put it here. Therefore, I will have r n x is less than or equal to 1 upon n plus 1 factorial. The maximum of x to the power of n plus 1 in this interval is at half. So, 2 to the power of n plus 1, that comes from here, and let us do one more simplification. I will insert here 2 into 4 into 6 into 2 n, all the even terms I will supply, so that this numerator will become 2 n factorial. So, I can make this as 2 n factorial in the numerator. Now, I multiplied by in the denominator 2 into 4, I multiplied 2 into 4 into so on 2 n. So, I will have this in the denominator here, but this is I can take 2 common here, each factor a 2 from here, 2 from here, 2 from here, 2 from here, that is n terms are there, 2 to the power of n, 1 into 3 into 3 n, that is n factorial. So, the denominator will be 2 to the power of n, n factorial, and this 2 to the power of 2 n plus 1 by half. And this should be less than, we are given the 5 into 10 to the power of minus 3, 5 into 10 to the power of minus 3. Now, it is a matter of simple cancellation and using the calculator, because these are all factorials involved, using the calculator by setting an integer value n, and we can find out when this particular value is less than 5 into 10 to the power minus 3. In this case, the example comes out to be n is equal to 11 comes, n is equal to 11 is the value that is required, and therefore, number of terms is 12, is n plus 1, that is equal to 12 terms. This is how the Taylor series can be used. However, the Taylor series is not the one that is commonly encountered. The most commonly encountered problem, we shall call it again as interpolation, is the data given to us, a table of values. As I said, two types of problems are encountered. We are given x f x, x naught f at x naught, x 1 f at x 1, so on x n f at x n. Therefore, we are given n plus 1 data values. We could also call in the 2 dimensional plane, this is a point. So, we can also say n plus 1 data points are given. Now, first of all, we know that in the 2 dimensional plane, if 2 points are given, I can always pass a straight line through these 2 points. So, this is a straight line. That means, given 2 points, I can always construct a linear polynomial to go through those 2 points. Therefore, we have through 2 points, they are distinct points. These are n plus 1 data points, but let us make it clear they are all distinct points that we are considering. Through these 2 points, a straight line let us call it as P1x, polynomial of degree 1 x can be constructed. Through 2 points, a straight line, a P1x can be constructed. Suppose now we have 3 points. Now, if I have 3 distinct points, I can try to pass a parabola. These are the 3 points. I can try to pass a parabola through this. That means, a polynomial of degree 2 can be constructed, even though there may be a degenerate case in which all the 3 points may lie on this on a straight line. Therefore, through 3 points, a polynomial of degree less than or equal to 2 can always be constructed. The degenerate case is a straight line, otherwise we will have as a second degree polynomial, that is a parabola. That means, a polynomial of degree less than or equal to 2 can be constructed. We can construct a polynomial of degree 2 like this, which is of course a parabola, which is a parabola in 2 dimensions. As I said, the degenerate case would be that all the points are lying on the straight line. Therefore, I can have a polynomial of degree 1 which is passing through all the 3 points. Therefore, in general I now have n plus 1 points. Therefore, through n plus 1 points, a polynomial of degree less than or equal to n can be constructed. Now, the existence of this can be proved mathematically also. Let us suppose this is our P n x is the polynomial of degree n, which is given by a naught, a 1 x, a 2 x squared, so on a n x n. Let us suppose this is our polynomial. This polynomial is fitting the data n plus 1 data. So, it fits the n plus 1 data x I f x I is equal to 0 1 n. That means, this polynomial is exactly satisfied by this. Therefore, let us substitute the values x 0, x 1, x 2, x n here. So, we will have here f of p n at x I x naught, that is f x naught, is a naught, a 1 at x naught, a 2 x naught square, a n x naught to the power of n. Similarly, x 1 also satisfies. Therefore, we will have a naught, a 1 x 1, a 2 x 1 squared, a n x 1 n, and so on. We will have f of x n, a naught, a 1 x n, a 2 x n square plus a n x n to the power of n. Now, you can see that this is a system of n plus 1 equations in n plus 1 variables a naught, a 1, a 2, a n. We have to determine a naught, a 1, a 2. If the unique solution for a naught, a 1, a 2, a n exists, then this polynomial exists uniquely. Therefore, I need to determine this a naught, a 1, a 2, a n, and for that we need to have n plus 1 equations. These are n plus 1 equations in n plus 1 unknowns. In n plus 1 unknowns, a naught, a 1, a n. Now, the condition for the existence of this will be the determinant of this coefficient should not be equal to 0, then the solution exists. So, the condition for this is, therefore, we will have the existence condition or condition for existence of non-trivial solution is the determinant of 1. I am just writing the coefficients of this system, that is 1 x naught square x naught n, 1 x1 square x 1 n, 1 xn square xn to the power of n. So, that will be 1 x0 x1 x0 square x0 to the power of n, 1 x1 square x1 to the power of n, 1 xn squared xn to the power of n. This determinant has a name, it is called Vandermonde's determinant. It is called the Vandermonde determinant. Now, we can expand this determinant by the rules of the evaluating the determinant. I can subtract the first row from the second one, and then you can take common x minus x naught, x2 minus x naught, xn minus from the rows, and I can simplify this. And this is a very trivial case. Value of the determinant is the product of all xi xj I comma j going from 0 to n, but I greater than j. I am taking x1 minus x naught, x2 minus everything common. Similarly, I will have all the factors that comes into the product is this one. We have started the problem with saying that these points are distinct points. So, the data was distinct. So, distinct xi. Since there are distinct xi, xi minus xj is never 0. Therefore, this is not equal to 0. Since this is not equal to 0, we have proved that the solution exists. Therefore, this a unique solution exists. Therefore, we are now determined that this polynomial can be determined uniquely, but I would now like to show that the polynomial is unique. We have now shown the solution for a naught, a1, a2, an exists and it is unique, but I want to show that this polynomial also there cannot be more than one polynomial which can fit the given data. So, the polynomial is also a unique polynomial. The interpolating polynomial is unique. Interpolating polynomial p n x is unique. The proof of this is just 2 lines. Let us assume that there is another polynomial. Let p n some star x be another polynomial which fits this given data, be another polynomial which fits the data. That means, we are talking that p n star of x I is equal to f x I for all I. Then let us define the difference between these two polynomials as a function q x. Define q x is equal to p n x minus p n star of x. Now, p n x is a polynomial of degree less than or equal to n, p n star x is also a polynomial of degree less than or equal to n. Therefore, this is a polynomial of degree less than or equal to n. This is a polynomial of degree less than or equal to n. Now, let us see what happens for q x at these values x I. Therefore, q at x I is equal to p n at x I minus p n star at x I. Both the polynomials are fitting the data data, therefore, this is f x I, this is also f x I, therefore, this is equal to 0 for I is equal to 0 1 to n. Now, you observe that q x is now vanishing at n plus 1 points. Therefore, q x has got n plus 1 roots or n plus 1 zeros. Therefore, q x has n plus 1 zeros, but q x is a polynomial of degree less than or equal to n only. Therefore, the only possibility is that q x is trivially 0 or identically 0. Therefore, q x has n plus 1 zeros at x I. But q x is a polynomial of degree less than or equal to n, and it is having more number of zeros. Therefore, the only possibility is that q x is identically equal to 0, and when once q x is identically 0, we will get p n x is equal to p n star x. That means, p n x is equal to p n star of x. Therefore, the interpolating polynomial is unique. In other words, what we want to state here is that we will see it later on also, we shall be constructing the polynomial using different methods or different ways. The form of the interpolating polynomial can be different, but when once you simplify the whole thing and bring it to the form, they both will be identical. Therefore, we cannot have two interpolating polynomials for fitting a data, but all of them will be the same, but the form in which you write down the polynomial would be different. I mean, one may write it in a ratio form, which when simplified and this, or you write down in a different form, in a product form, it will be in a different form, but all of them would be identically same when you bring out everything into the expanded form and write it. Therefore, in that sense, interpolating polynomial is unique. Let us now construct the interpolating polynomial. The most fundamental interpolating polynomial is called the Lagrange interpolating polynomial. Now, let us again take the data as the given data is x I, f x I, or let us use a short notation x I f I is equal to 0 1 3 n. This is the data given to us. Now, if I want to construct a polynomial that fits this data, this polynomial must be a combination of f I. It must use all the values f 0, f 1, f 2, f n. Therefore, it should be a linear combination of all f I. Therefore, the polynomial is a linear combination of f I. That means, it should be of the form p n x is equal to some, I will write it as L 0 x, some function of x into f x naught. That is because it is a polynomial of degree n in x. Therefore, these f x, f 1, f 2, f 3 they are all numbers, they are all constants. Therefore, L 0 x into f x naught plus L 1 x into f of x 1 plus so on L n x is equal to f x n. Now, as I said, this is a polynomial. What we want here is a polynomial of degree less than or equal to n. f x naught, f x 1, f x n they are all numbers. Since these are all numbers, the only possibility is that L 0 x, L 1 x, L n x all these must be also be polynomials of degree n, polynomials of degree n. Now, the less than or equal to n we shall not put it here, it is n. If it is less than n, when you simplify this f x naught, f x 1, f x n they are all numbers, When you simplify, automatically the leading terms would cancel and it will agree with the left hand side. Therefore, these L0, L1, Lnx must be polynomials of degree n in order that the given data can be represented by an nth degree polynomial. But if this is the polynomial, this is fitting this data. So, let us just satisfy, that is Pn of x naught must be equal to f x naught, but this is equal to L0 x 0 f x 0, L1 x 0 f x 1 plus 1 Ln x 0 f x n. Now, this should be equal to f x 0 only. Therefore, I cannot have f x 1 f x 2 because this is a identity. Therefore, this should be containing only this. The only possibility is that L0 x 0 must be 1 and all this should vanish, only then this will be equal to this one. Therefore, this implies that L0 x 0 must be 1 and all other values L1 x 0 must be equal to 0, so on Ln x 0 must be equal to 0. Only then this is going to be same as this particular polynomial. Let us do one more and generalize it. This is f x 1, L0 x 1 f x 0, L1 x 1 x 1, Ln x 1 f x n. Yes. Now, if this is to be again to be equal, f x 1 is here, f x 1 is here, the only possibility is L1 x 1 must be 1 and the remaining all else should be 0. So, this would imply that L1 x 1 must be equal to 1, L0 x 1 is equal to 0 and this is L2 x 1 is equal to 0, so on Ln x 1 must be 0. Therefore, it is possible for us to immediately generalize it by just writing xi is equal to f xi, that is L0 xi f x naught plus Li xi f xi Ln xi f xn. Now, I can generalize from here that this Li xi will be 1 and all the remaining will be 0. Therefore, I would get the result that Li xj is equal to 0 for I not equal to j, this is equal to 1 for I is equal to j. And those who are used to the notation of Kronecker delta, we can write this as simply delta ij. So, this is the Kronecker delta, this is the definition of this is that it is equal to 0 when I not equal to j and when it is will be equal to 1 when y is equal to j. Therefore, all these polynomials they should satisfy this, and these polynomials are called the Lagrange fundamental polynomials. Lagrange fundamental polynomials. We shall actually construct the form of this Lagrange fundamental polynomial using this idea from here, and we will be able to construct the Lagrange interpolating polynomial from there. I think we should stop from this, please.